So just before I start it, I didn't put the square bracket on this number here because I'm including it, and the 0 I'm not, so that's a round bracket. So I didn't make that clear at the end of the last lesson. So if you have it in your notebook, just make sure it's a square because you are including this. If it equals 0 here is the problem. Please turn, next page. It is, yeah. Alright, you got that? So next lesson we're looking at types of mappings and functions. No, it's okay. So we've seen, what's wrong? We've seen a small example of this already. We said when the range equals OR, we call this function onto. This is a type of a function. In fact, we can have our functions that are one of 4 possibilities. So there's a little bit of vocabulary in this lesson to go through first. So firstly, we know domain. So our first definition needs us to use the word domain. A mapping F is a rule that takes one element from a domain, and returns to us something from the codomain. So this all seems very complicated, and it's really the easiest way I can write it, but I think with a diagram it will help a little bit. So in your head you picture this is our domain. So maybe this is all the real numbers. So there you go. There's 2, there's 3, look, there's 4. They're all having a great time. So there's all our real numbers in the domain. Yep. And our function, our mapping, what it does is it takes one of these numbers and basically gives you something back in the codomain. So in this example here, maybe the 3 gives me a 9. Maybe the 2 gives me a 4. Maybe the 4 gives me a 16. You've actually seen, you know what this function is. What is this function? It's the squaring function, yeah. So this is really about vocabulary just for the moment. This is called the domain, and this target is called the codomain. Yes, now this is where you have to be careful. The range is not quite the same as the codomain. Does anyone feel they might know the small difference between the range and the codomain? And if it helps, this is like what we call a space, and this is like a space, you know, from one space into another space. Does anyone feel they might know the small difference between range and codomain? No? So it's really, really a small difference, but the range is inside the codomain. And sometimes the range actually does equal the codomain, but not always. So with our example of the x squared function, what's the domain for x squared? What's the domain for x squared? All real numbers. And what's the range?
All real numbers.
No?
No, positive numbers.
Just positive numbers. So on my diagram here, in red, this is actually the range. But in fact, we call the whole thing here, the whole space, is called the codomain. So the range is just a part of the codomain where the answers live. But the codomain is like the space. So if you want to compare the codomain is like the house, and the range is the rooms that people sleep in, But if it's a hotel, then everybody sleeps in every room. So sometimes it is the full thing, and sometimes it's only part of it. And maybe that's actually good for our first definition, maybe, but maybe we'll just leave it at that for the moment. It has a special name when the range and the codomain are equal. This has a special name as well, but we'll get to that in a minute. Guys, what's wrong? Come on, I need you focused here. Unless you know this already. Do you? No. Anybody? So, let's have a look here at some examples, and just another bit of notation. So in the domain here, there's only 3 elements. I'll call them A, B, and C. And in the codomain, there are only 3 elements, X, Y, and Z. And let's just suppose f of A, that gives me Y, f of B, that gives me X, and f of C, that gives me Z. If your function does this, if it gives you one special unique value for every unique value that goes into it, we call this function one-to-one. This is a one-to-one mapping. So in other words, if x1 does not equal x2, then you want the function to also be different. Is x squared an example of this? What do you think? No, why not? Not quite that. What is 1 squared? 1. And what's minus 1 squared? 1. Did you get the same answer or a different answer? Same. 1-to-1 needs every answer to be different for every number you put inside of it. What about EX? What do you think? What do we think? It is. And what about sine x? It's not, because sine of 0 is 0, and sine of 2 pi also 0. By the way, for the graph, what you need for the graph to be able to tell is the graph should always be increasing, never increasing then decreasing, or decreasing and increasing. So for example, this is not 1-to-1. It's like what? X squared. Because here, for example, here's x and here's the value for y, and then here's a different x, but, why do you get the idea? The same value of y. Anyways, I don't want to go too much on a separate point here, but just the key idea here is 1-to-1 means for every different value that goes in, you get a different value that comes out. Alright, so let's look at our next example, because I said there's 4 types. Alright, so again, we'll do x, y, z, and here let's, call it u, v, W, Z, something. So X goes to U, Y goes to U, and then Z goes to Z, something like this. This function, this is many to 1. You can probably guess the reason why, because you can have many different values producing the same value. So for example, if some x1 does not equal x2, but fx1 equals fx2. So x squared, what do we call this? We call this one many to 1, because 1 and minus 1 will give me the same number. 2 and minus 2 will give me the same number. Yeah? Okay. So this is many to 1. Can I scroll down? Not yet? Okay. So just give you a minute. I'll talk more about the graphs in a moment, but for many to 1, what's a feature of the graph is that usually it increases and then decreases, and this is how come you get two different values but the same y value. But in a moment we'll talk about the graphs, don't worry. Okay, so that's many to 1. Yes, okay, so next example now. Next example is this. A, B, C, X, Y, Z. So let's say A goes to X, A goes to Y, C goes to Z, and let's just put in another value here, U. B goes to U as an example. So this one here is 1 to many, because if you look at the A, you have one A, but you have two values for A. A could go to X or A could go to Y. So this is called, this is 1 to many. So this is when y1 does not equal y2, but fx equals y1 and fx equals y2. Or another way of saying it is that fx equals y1 or y2. So this is a 1 to many mapping. So you're all smart. You can probably guess the name of the last one. Yes, many to many. So the last one is many to many. And you might even be able to guess what it would look like. So before I draw it, why don't you try and draw an example yourself if you think you can guess the last one, many to many. And then I'll draw it here in a moment. You can see it's the same. Okay, I'll draw my one now, and you can see if yours is similar. A, B, C, I'll just go with, and then X and Y. So, A to X, A to Y,
Each one goes.
yeah, B to X, B to Y, and then C to X, and C to Y. So you can see that A, B, and C, they all go to X. Don't they? Yeah, A goes to X, B goes to X, and C goes to X. So that makes it the many to one part. But also, A goes to X and A goes to Y. So that makes it the one to many part. So together, we say this is many to many. This is a many-to-many mapping. Although a lot of A-level books, I don't know if it's just me or if it's just difference between UK, Ireland and US, but a lot of A-level books would just call it one, many, you know. But for me, I'm always used to putting two in the middle. So 1 to 1, 1 to many to 1, many to many. But if I'm just saying, if you look at a website or an A-level book, it would probably just call these many, or 1, 1. But at least when I say 1 to 1, I hope you can feel like the definition is in the word. It's 1 to 1, or 1 to many. Okay, so this is a many to many mapping. Notice I'm using the word mapping, which you might say, isn't that the same thing as a function? In fact, not quite. Only two of these definitions are for functions. Which two do you think? So I'll just write them down here. Hang on. Oh, so there. Many mapping and function, and we have 1 to 1, 1 to many. Many to 1, many to many. Mapping and function are almost the same thing, but we just need to be careful with our vocabulary. And in fact, they're not even careful about this in the exam, which they should be. If something is 1 to 1, we can call it a mapping or we can call it a function. So for example, my first one was 1 to 1. I can call that a mapping or I can call it a function. 1 to many can be called a mapping but not called a function. So we don't consider this a function. Or at least we don't consider it a good function. Many to 1 can be called a mapping or we can call it a function, and many to many can be called a mapping but we cannot call it a function. In other words, the too many part is bad for us for functions. Which is interesting because it means fx equals square root x. I can call this a function. But tell me why I cannot call this a function. So one is a function and the other is not. This is not a function. Why not?
Because it's
Yeah, well, what type is it? It is 1 to many.
Yeah.
For example, here, if I put x is 9, what do I get for the answer? 3. And will I ever get 3 again if I use a different number? No, only square root of 9 gives me 3. So this is 1 to 1. So we can call it a function. If I put 9 in here, what do I get? Plus or minus 3. This is 1 to many. Therefore, we should not call it a function. We can call it a mapping, though. They are not always careful about this language in the exam, unfortunately, but I like to be careful with this. So just as a note here, all functions are mappings, but not all mappings are functions. So we can call this a function or a mapping, but we can only call this a mapping. We can't call it a function. So let's talk a little bit about the different graphs. So we have, what does a graph of a one-to-one function look like? A one-to-many, a many-to-one, and a many-to-many. Okay. So firstly, a one-to-one. So here are the features of a function which is one-to-one. Basically, it's this, that it's always increasing, or possibly the opposite, always decreasing. This makes it one-to-one. So you can immediately think of some functions which are one-to-one. Give me some functions which you can know that graph in your head that are one-to-one. So linear, right? Just like a straight line going up. What else? Yeah, but only certain types of cubics. So x cubed is, but only x cubed. We'll talk about that in a moment. Anything else? Think of functions that are always going up. Square root x, actually, yeah. E power x. Anything else? What's that? Well, not x squared though. Oh, something power x. Yes, okay, something power x. Yes, yeah. 2 power x. Yeah. What about log x? Yeah, log x will always increase. Right. Let's have a look at many-to-one now. So, what are the features of a many-to-one graph? Well, basically the feature of a many-to-one graph is that it looks like it has some kind of turning point. Or maybe more than one turning point. And another way to tell if it is many-to-one is as follows. Can I draw a horizontal line that cuts the graph twice? Yes. Or at least twice. So here I could actually cut the graph 3 times. So this makes it many-to-one. Whereas in my last example, if I draw a horizontal line, how many times do I cut the graph? Just once. Whereas here I can do it more than once. This makes it many-to-one. Okay, next example is one-to-many. And the key thing about one-to-many is it has 2 heights. So another way of thinking about it is if you draw a vertical line, you should meet it more than once. In this case, twice. That's the many part. And again, if I go back to my first example, if I draw a vertical line, it's only once, isn't it? And here, if I draw a vertical line, it's only once as well. But here, if I draw a vertical line, how many times? Twice. So this makes it the one-to-many part. If vertically, you can make it cut twice or more. So for example, this here. That would also be one-to-many. So the last one is many to many. I scroll down. Many to many, and it's usually something that looks like this. That if you draw a vertical line, you can make it cut twice, and if you draw a horizontal line, you can make it cut twice or more. This is many to many. Sometimes in the exam, for 4 marks, they give you 4 graphs, and they ask you to write the name of the type of graph it is underneath the picture. So I recommend drawing horizontal and vertical lines, and this will be the quickest way to tell. So you go to the exam and you go 1 horizontal, 1 vertical, 1 horizontal. Okay, 2 horizontal and 2 vertical. This is many to many, for example. Okay, let's have a look. We'll just do everything I've done so far prepares you to do question 1. And I'll just do A and B from question 2 just to give you the idea, and then we'll finish. Now, in question 2, I ask you to tell me if the function is 1-to-1 or many-to-1. So can you just give me the first function, 2a? What is the first function? Yeah? Now you already know the answer. What is the answer? Is this 1-to-1 or is it 1-to-many? 1-to-1. But that's because it's linear and it's easy to see the graph. I'm going to show you a method that will work for all problems that you can check the answer. Again, just like earlier today, if you want to use a graph, no problem. But that only works if the graph is easy to do. The method I'm going to show you works for all problems. So the first step is you say x1 does not equal x2. Step 2 is find any x1 and x2 so that fx1 equals fx2. And step 3 is the answer. If you can find x1 and x2, then that means it is 1-to-many. And if not, that is 1-to-1. So in other words, what you do is you say, okay, I have 2 numbers which are different. Let's see if I can make the function value the same. If I can, then I've definitely shown that it is 1-to-many. If I can't, then it's possible that it's 1-to-1. I can show it. So let's look at this example. Okay. I can scroll down. Okay. So we have fx equals 6x plus 8. x1 does not equal x2. Let's see if I can solve this. So this is step 1, this is step 2. So I have 6x1 plus 8 equals 6x2 plus 8. That means 6x1 must equal 6x2. That means x1 must equal x2. Can you give me a number so that x1 equals x2 and x1 does not equal x2?
0.
No. Impossible. What am I asking you to do? I say give me 2 numbers so that they are equal and also at the same time different. Yes, it's impossible. Yes. So what does that mean if it's impossible?
1-to-1.
Therefore 1-to-1. I suppose you should write a sentence at the exam. You should say, it is impossible because of this result here and this result here. We can't pick numbers for both of them to be true. We can only make one of them true. We can't make both of them true. Yeah? You don't look happy, Brandon. Is okay? You're happy? Oh, good. Okay, last example. I'll do the next one as quadratic. Can you just read out the quadratic, please? Fx equals... It is quadratic, isn't it?
Mm-hmm.
What is it?
2x squared.
Yeah.
Minus 4x
Minus 4x.
minus 6.
Minus 2. Now, if you picture the graph for quadratic, what type is it? It is one... sorry, I'm getting my words mixed up. Many to one, isn't it? Isn't that what it says in the question?
Yeah.
Yes, many to one. So you can have many values going to the same one value. Like our example with the 1 and the minus 1 squared, they both go to 1. Alright, so let's have a look at the method here. Step 1, x1 does not equal x2. Step 2, fx1 equals fx2. So that means 2x1 squared minus 4x1 minus 2 equals 2x2 squared minus 4x2 minus 2. What can I cancel? Well, the 2's go here. So I have 2x1 squared minus 4x1 equals 2x2 squared minus 2x2. What can I cancel now? I can divide everything by 2, so now I have x1 squared minus 2x1 equals, oh sorry, I dropped that should be a 4 there, x2 squared minus 2x2. Here I'll factorize. This is x1 times x1 minus 2 equals x2 times x2 minus 2. So I would like you to give me two numbers which are different, but this is true. So what do we think? So give me a number for any number for x1 and x2 so that they are different, but this is true.
0 and 2.
Very good, 0 and 2. I have 0 and 2 different numbers. Of course, one is 0, the other is 2. They're different. If I put 0 in here, what do I get? 0. If I put 2 in here, what do I get? 0. Are they the same? Yeah, so was I able to find two different numbers here? I was successful. So what type of function is this? Many to one. There is a way you can check the answer. Look, just to finish. This is how you check the answer. If you put 0 back into the original, what do you get? Minus 2. And if you put 2 back into the original, you'll also get minus 2. So we have shown that 0 and minus 2, they go to the same point on the y-axis. So it is many to 1. Lunchtime.